to our fourth lecture on scientific computing in Python. Before we actually start with the lecture, I have some announcements to make. So, first of all, Chris invested some time and prepared these wonderful shell tutorials for you. So, in case some of you still having or experience problems in navigating through your system with a shell, they're on StudIP on the tab courseware. There are now a bunch of videos that you can view to recap that. And what else do I have there? Yeah, and exactly. So this is our lecture here. So if you go to Scientific Programming US, there's a lectures repository, and there you find here week 4 NumPy lecture, and then you can click on the IPython IPython notebook, and that will render also in the browser, or you run it locally with Jupyter if you want to follow along. So by now you hopefully have a thorough understanding of how the basic Python programming language works and how to do basic stuff and use even some of the advanced features. So basically today we start with the real scientific part of the lecture as we introduce NumPy. So NumPy is a Python package for dealing with large numerical data, basically offering very flexible ways of manipulating the data and also very fast and efficient ways to do mathematical computations on this numeric data. Yeah?
Could you first zoom in a bit and second maybe make the speakers a bit louder, I think?
Okay. Where can I do it? Yep. Bühnenlautsprecher, so is this now louder? Medienton? No, that's Umhängemikrofon. Ah. Now? Okay, so that's good. And what was the other request?
Control plus.
Oh, make it bigger. I think this. Is that fine for everybody to read? Okay. Yeah, so we basically start with an introductory example. So to basically demonstrate why we even need a package like NumPy. So basically we know Python has this container type called list where you can basically store any data type that you want, and you can make you can put lists into lists and basically use as multi-dimensional arrays if you really wanted to. So what we basically do here, we'll create a bunch of 1 million random numbers, random integers. By the way, this is a very nice thing that you can do in Python 3.6, that you put underscores in your numbers so you can basically make them more readable. And then we just want to calculate the mean over this 1 million random numbers. And we have this kind of naive implementation here where we just sum up all the values with a loop, and then in the end we divide by the number of values that we have. And in the end we time how long this is going to take. So we time and wait and wait and wait for some time. And what you can already see that this is probably a little too slow. If it already with 1 million integers it takes this long, then you probably don't want to handle even bigger amounts of data where you have to run more complicated computations than just calculating the mean. So exactly for this reason NumPy was invented. So to demonstrate here how NumPy would work, basically why is this the case? Why is this so slow? So the problem is that Python is designed for basically being very convenient to use. So what happens, for example, if you divide by 0, you get an error. If you what I think we showed you in the first lecture, if you have the biggest integer that can be represented in a system and you add something to it, then it just still gets bigger because it changes its internal representation. So basically Python does a lot of checks for you that you don't shoot yourself in the foot. On the other hand, of course, these checks take a lot of performance. So basically what happens here when we do this add operation, the interpreter has to check every time that the type of this accumulator variable and the type of this measurement variable here are really the same and can be somehow added together. So not with the same, that one is suddenly a string and would have to raise an exception. So but on the other hand, we know that in this case we really just have 1 million integers. So if we could somehow just tell the interpreter, okay, and I know I'm only dealing with integers here, I could somehow we could make use of optimizations and speed up this operation. So that is really what NumPy is doing. So to use NumPy, we import NumPy usually as NP, so we abbreviate the import This is something we should like really only do if it like has a strong convention in the community. So this is really like what everybody does, but you shouldn't now start to like abbreviate every import that you make as a two-letter code, because then it becomes somewhat unreadable. But basically everybody knows it, and P stands for NumPy, so that's fine. So and what we then do is we create a NumPy array just by calling the array constructor on that list that we had before. This is all you do, and then you see, okay, instead of a list, we now get an array that contains all the numbers. And we can look at the type and see, okay, this is type ND array, so that stands for n-dimensional array. And now it contains all the numbers, okay. And basically, NumPy arrays work more or less like Python list, basically. So you can index them as you're used to. You can access single elements, you can slice them. What is different to list really is that they suddenly have a data type. So there's this attribute dtype, and you can see, okay, this array has a data type in 64. So basically, the array knows that all the values it contains are really integers. So this is really what NumPy makes use of when we do like calculations. So we can use this npmean function that is inbuilt to calculate the mean, and suddenly we will see that it should be much faster. So this is like 4 milliseconds. With the plain Python implementation, it was like 146 milliseconds. So this is, in this case, a more than 100 times speed up, I guess. No, not really, but somewhat in that order. So with this, I hope you are convinced that NumPy is really necessary, that we don't want to rely on plain Python types to do really computive intensive tasks. And so we'll basically go through the basic things that NumPy arrays offers and how you can operate with them. So first of all, we talk a little bit about, yeah? Oh yeah, that's a good idea. Well, where can I turn off the lights?
On the switch on the door.
Okay, that's better. Not too dark. Okay, so we'll look at some of the attributes that basically NumPy arrays offers. So what we already saw, like they have a D type, and this information gives, this attribute gives information about the data type of the values that are stored in that array. So, for example, we can explicitly name this data type and say when we call the array constructor, okay, here, make the data type explicitly an integer. And then we really see that also the data type is in the end an integer. In this case, it's an integer of 64-bit size for each integer. We could also have other data types like floats of different sizes, or also just bools. Where we say, okay, now if you want to make a data type that's bool, then suddenly we just get an array of false and true, even though we had here values from 0 to 4, but basically every value is then interpreted as this data type, so we know that only 0 is interpreted as false, everything else is true. So this is what we get in the end. Now what happens if we have a list of mixed data type that we input to the array constructor? Then basically NumPy will figure out like what's the highest data type in this list. So basically here it will be floats, because we have a mixture of integers and floats, and also integers can be represented as floats, but not the other way around, so we just make all values floats. You can see also that the data type is float 64 then. However, once the data type is set on an array, it cannot be changed afterwards. So basically what happens if we have our integer array from before and now try to assign a float to a particular place in that array, it will be coerced to the integer type. So it will be just cut off whatever is beyond the decimal point and will be interpreted as a plain integer. So, and really these data types that are now stored in the array are no longer these Python data types that are so convenient and catch all the errors, but are really like more or less plain C types. So basically they only have this amount of memory that it says here to represent themselves, and they are also dense in memory, and so this really makes it necessary again to think about like basic things that we can basically forget when we just deal with plain Python, like for example overflow. So we have one question here. So we make an array of unsigned integers of 8-bit size each, looking like this. So we see now the data type is only int 8, and now we add 255 to entry 1. So anyone, what will be the result of this operation? 1 plus 255, yeah.
0.
Yeah, exactly. So because with 8 bits we can only represent values from 0 to 255. If we add 255 to 1, we get 0 again. So basically the whole representation wraps around. So this is something you should be aware of when you operate with NumPy arrays, that these errors are not caught for you anymore. So usually we don't have 8-bit integers with 64 integers, and then what we can represent is very large again. So we usually don't hit these boundaries, but we should basically keep in mind that these things can occur again. Okay, and the other attributes that arrays have are shape and endim. So basically, the shape of an array tells us how many values we have in each dimension. So if we just make a simple array with 5 values, then the shape will be just a tuple of, let's say, 5. Because we just have a single dimension and 5 values in that dimension. So, and respectively, the endim can be viewed as the len of the shape, and just tells us how many dimensions we have. So we just have a single dimension, right? Because we just have this here. This is just a one-dimensional thing. So now, if we go to 2 dimensions, so we can have this list. We multiply it by 3, and then we input this to the array constructor, and we get basically an array that looks like this. So we can see that we have more square brackets here, so this is a 2-dimensional thing. So the shape of that is then 3 by 5, because like in the first dimension here we have 3, and then we have 5 values in the second dimension. And respectively the endim attribute then goes to 2. And you can basically view the number of dimensions as like how many indices you can provide to basically get to a scalar value. Yes?
If I want to do scalar multiplication, so if I want to do scalar multiplication, scalar being 3 to this vector, what should I type in?
We'll come to that later. So basically this is very convenient with NumPy. You could just do something like this, and then the whole array would be multiplied. This is basically just for creating input data to have a 2-dimensional array here. So as you might know, for lists, this is what will happen if you multiply a list by 3. It just like replicates a list by 3. And this is just afterwards we input this to the array constructor, and then we get a NumPy array that behaves differently for this kind of multiplication. But we'll come to that later. Okay, and this basically just continues. So if we make a 3-dimensional array, we can get something like this, where you have now 3 square brackets, and then we also have a shape of 3 and 3 is where we have suddenly 6 in the first dimension. So you see that we have like 6 blocks here. So this would be our first dimension, and the second dimension is the row we choose, and then the third dimension is like which column we choose here in this block. And then respectively the dimension is 3. And this is just very basic stuff that every basic attributes that every array has, and that are very useful if you are dealing with arrays, that you can check if your arrays still look like you expect them to be. So next thing will be on creating arrays. So we cover a few utility functions to create arrays from scratch, because by now we always created Python lists first and then put them in the array constructor. But of course, if you already know what kind of array you want, it's somewhat unnecessary, right? You first create a Python object, then you put it into NumPy, then the Python object gets thrown away, and then you just keep the NumPy array. You could also just create the NumPy array right away. So a very useful function here is nparrange. So it basically works like the built-in range function from Python. So just type in a number, and it gives you all the values from 0 to 1 minus the argument in steps of 1 as an array in this case. And you can also extend this like the standard range function, giving start, stop, step arguments, and then yeah, it will basically change the way it generates its values. In this case, making steps of 2. Also very useful is linspace. That is somewhat similar, but instead of start, stop, step, you have to specify start, stop, num. So it will basically give you linearly spaced values between -5 and 5 in this case. So we see here that then the first value is -5, the last value is 5, and in total we get 10 values in here. So it will somehow figure out basically how these values should look like. Yes?
And the array is called array? So that's the name it gets, or?
You mean this here?
Yeah.
So this is just a string representation of an array. So right now, if we just call this function, it just returns an array. And then this array is displaced because it's like the last argument in this cell here. But the array itself is now called nothing. It's just a Python object. It gets like spit out and displayed here, and afterwards, because we did not bind it to a variable, it's destroyed again.
Okay, and if we want to bind it, we just state name is and then np.
Yeah, we would just like any Python object, you just bind it to a variable, you do this and nothing happens, and then you can just output A again. Yes?
In NumPy range, is the stop exclusive or inclusive?
In stop, there is stop is exclusive.
So if it would be 14, the output would be the same.
No, right now we have 13 and it goes only to 12.
So if the stop would be 14, the output of the array would be the same, right?
No, the output then would have. Okay, in this case, yes, because we have a step of 2, that's true.
Yeah,
okay. Okay, just like if we have a step of 1, then the output would be different. Okay, yeah. Any other questions? Okay, so this is when you have like a range of values that you want to cover. If you just want to make an empty array where you want to fill in values later in, you can use utility functions like, for example, zeros. So as the name says, it just gives you an empty array filled with zeros. So in this case, you get like an array with 5 zeros in there. Also, this function takes, so this basically is just a scalar value. You can also input a tuple as a shape, and then you just get an array of the shape that you put in there. So if we put in 2 times 3 times 2, you get a 2 times 3 times 2 array full of zeros. Yeah, and the default data type here is float. If you don't specify anything else, you could also specify the data type that you want here. So basically these also exist with others, like with ones. So if you want an array filled with ones, you can do the same. And if you don't know what you want, you have basically like 2 options. You could either use zeros and try to fill up everything later, or you use empty. The problem with empty is that it will just like take whatever is left in memory, because yeah, basically what we did here, we created an array filled with ones, and then we discarded it again because we didn't save it in a variable. Now if you call empty with like and want an array of the same shape, it will look in memory and say, okay, give me just whatever bytes are left there and I use them for my array. So suddenly here everything is filled with ones, even though we did not explicitly say we want ones. So I think like if we execute this first and then execute empty again, it's now suddenly filled with zeros. So the problem is like empty is kind of fast, of course, because it just takes a block of memory that is left and says, okay, I will now use this as an array, but then you should really make sure that you overwrite every element that is in there later on, because so you're not surprised by whatever suddenly is there. So it could also be that there's just some garbage left in memory and suddenly you get numbers of 1 million or so. So I would actually recommend, instead of empty, just using zeros, because then you at least know if you forget to basically overwrite the value that there's a zero and not something that could be anything by surprise. So and then finally, if you want an array filled with a certain value, you can use npfull, and then you just specify the fill value and the shape, and then you get like an array full of these values. And often what is needed is like using random values. So NumPy has a wonderful random module, and there you find basically numbers for generating random values from all kind of probability distributions, so normal distribution, uniform distribution, and any other stuff. So in this case, just a random function just gives you numbers between 0 and 1 randomly distributed. And here also you can specify a shape, and then you just get like an array of shape 3 by 3 filled with random values. So this is really just like the basics for creating NumPy arrays. now we actually get to the more interesting stuff of doing mathematics with NumPy arrays. So we just create a simple array here for demonstrating the stuff, and then as you already asked, so what do I now do if I, for example, want to multiply this with a scalar? So we can also show this first. So we have an array and say we want to multiply it by 3. So as you saw with lists, it just gets duplicated. But what happens with NumPy arrays is that basically this operation is applied element-wise. So now every element in this array will be multiplied by 3, as you see. So this is a really convenient way to basically express formulas that operate on large data sets. And so basically this way of operating on data structures is called vectorized. So because usually, like if you have a list, you would have to write a loop and say, okay, for each element in this list multiplied by 3. Here basically the operation just happens that we view this as a vector, and just with writing one command it automatically applies it to all elements. So, and these functions are called NumPy universal functions, because I'm not sure if this is really the most universal thing you could do, but at least works on all elements. So single command, and they are abbreviated ufuncs. And basically these functions are also much faster than anything you could do in Python, both with using loops and using the standard math module. So in this way, yeah?
And if I already have a NumPy vector and I want to make a duplicate of this vector, then do I need to cast it to the list and then make a multiplication via 3 to duplicate it?
No, I mean, like if you just want to copy a vector, you can use so every vector or every NumPy array has a copy method, so you can just copy the whole thing, or you can also pass an array to an array constructor, and this should also create a new array. But if you just want to add two arrays, for example, like here, you can also add the two arrays to itself, and these operations will always create a new array. So this is now, right, we have this array, and so we just add here 0 to 0, 1 to 1, 2 to 2, and everything happens element-wise. And so this is the outcome. So and this basically works for any kind of standard arithmetic that you know from basic Python, so you can also subtract stuff. And then obviously if you subtract always the same numbers, everything is 0. You can also divide stuff, so everything should be 1, except for the first value, which is a 0. So here again we see this problem, like Python would give us a division by 0 error here if we try to divide by 0. NumPy just gives us a none value, so this basically is a central value to indicate that this is not a number. And in fact here it even raises a warning at least, so that it does not throw an error like Python would. So you need to make sure yourself that you don't accidentally divide by 0, or then at least deal with the results appropriately. So and then you can also multiply arrays, and you can also potentiate arrays or take the power of arrays. So this already, this all happens very conveniently. And in newer versions there's also this add sign, which is overwritten, which corresponds to the matmul special method. So this will basically, if you have a two-dimensional array, it will do like standard matrix multiplication. If you just have two vectors, it will just do the inner product between vectors. So as you probably know from linear algebra, right, the inner product is just like taking the product over each element and then take the sum over all these products, and so this is basically the same as now doing the add sign. So if you do a lot of algorithms or linear algebra, this is very convenient to write stuff down. Okay, so then we have some mathematical functions that you can also use.
Sorry, what happens if they don't have the same shape, the arrays, if you like do any operations?
So if that is the case, we'll cover that later, then something like broadcasting will happen. So NumPy will somehow try to align the shapes and make the arrays bigger where possible, and if this is not possible, then an error is raised. So, but we'll cover the exact details of how NumPy will try to make everything the same shape to be able to operate. Okay. So yeah, NumPy also provides a lot of like standard mathematical functions, so you can make logarithms, exponentials, and for example sine curves. So basically again here, you see that warning is raised because you try to take the logarithm of 0, and then this somehow defaults to minus infinity. So again, you have to make sure that you don't do operations that don't make any mathematical sense here. And again, here basically this this function is applied to every element in the array. So this would be like e to the power of 1. No, e to the power of 0 is 1. E to the power of 1 is exactly e, and then so on. Yeah, and basically you should always try to use NumPy functions if you want to do mathematical operations, because they're also faster. Basically all of this is written in C code that is very efficient and does not really use Python, which would be somewhat slow, so don't try to use functions from the math module if there's something available in the NumPy module, which basically is always the case. Okay, so next I will cover something called aggregation functions. So basically, aggregation function is anything that reduces the dimensionality of an array. So if you have an array of dimensionality 3 and then you call a function that reduces the array, what you get is an array of a smaller dimensionality, or even just a single scalar. So what we'll do here is we'll just make a two-dimensional array by calling this arrange function, make 16 values, and then on this we can call the reshape method. So reshape basically takes a tuple of a shape we want, and then it will basically try to cram this array that is there into this shape that we want. In this case, if we have 16 values, it's very easy to put it in a 4x4 shape. So we get this array. So what we can now do, for example, is take the minimum. So the minimum of this array is obviously 0. So and this can be viewed as a reduction or aggregation operation, because before we had an array of dimensionality 2. Now we have a, so to say, an array of dimensionality 0. In fact, we just have a single scalar. So if we don't want this to happen, to basically take the minimum over the whole array, but for example only over each row or over each column, all these aggregation functions basically take an axis argument. So with these axis argument you can basically specify which axis you want to reduce. So 0 would be like the first dimension that is there. So in this case, the first dimension would be the row. So if we, so let's let me maybe demonstrate this. So basically with the first, so with the first index that we supply, when we index this array, we choose like which row we look at. So this would be the first row, this would be the second row, right? So and if we now want to say, okay, we want to lose this dimension and say, okay, take the minimum over axis 0, then we basically take the minimum over this dimension, because this is what we choose when we supplied the first index. So basically what we get here is then the minimum over this thing, because like before, like we could choose here, but now we can't basically make this supply the first argument anymore. Now we can only choose a column, so that is why I took then the minimum over this dimension here. Okay, and does it make sense? Yes?
Does it compare every value, or does it just look for the minimal value and then returns the
So I mean,
line
like
with the
this depends on like how you call the function, right? In this case it just like compares every value.
So if you put, for example, a 1 where the 0 is in the array and then the 0 on another place, that line will be.
So I mean, if I put a 1 here,
Yeah.
then exactly, then this value would be 1, because then on this column then the minimum value would be 1.
Okay.
Yes.
So it adds up every value inside of one row. Then it, or
No, it doesn't add up anything, it just like looks for the minimum. So
minimum, it has to add up the values inside.
why do I have to
Is
add
it
up?
just the
So-
row containing the minimum? Is that what it's doing?
No, it's not taking the row, it's actually taking the value. So
Yeah, but the value of what? Of the whole row.
so wait, let me Do we have chalk here? Please do not.
Committed between the two.
Ah, oh yeah. So in this case, right, we had an array basically that looked like this here. We have like, just make it a little smaller. So then continue. I mean, I can also make different values. Let's say we have 5, 8, and 10 here. And then finally we have 22, 32, 42. And so it's basically our, can you read this with the beamer on? Okay, so now we say, okay, if we take the minimum over the whole thing, then it would basically just compare every value and look, okay, which is the smallest value in the whole array. So we look at, okay, 0 is very small, this is bigger, no, this is bigger, everything is bigger, so we say, okay, this is just 0 in the end, because it is the smallest value in the whole array. So now if we additionally say, okay, we want to take the minimum, but over x is 0, then it will in fact look on this zeroth dimension. So we said before, okay, this is the first dimension that we index, so this is dimension 0, this here. So and therefore it will look to reduce this dimension by basically looking for the minimum here, looking for the minimum here, and by looking for the minimum here. So then here we will basically look and see, okay, 0, 5, 22, which is the smallest value. So this is 0, and here's 1, 8, 32, so this is 8, and this is 2, 10, 42, so this is 2. So if we now, instead of taking the minimum, take the maximum, and again take this over x is 1, and we would get something like, okay, we look here, which is the maximum value, we get 22, 32, 42.
Okay, so if you would swap the positions of 1 and 8, you it wouldn't change
In this
the
case,
outcome.
in this case, it wouldn't change. But
Okay, it was just a little bit difficult to see because it's the same as the first
Yeah,
row.
okay.
So yeah.
I see, yeah.
What if my matrix looks like 0, 1, 1, 0?
So you mean if you don't have an explicit, or if you have two values that are minimal?
Would it sound the first one, or?
I mean, like in this case, it doesn't make any difference to you, right? If you want to take the minimum over an array that is like 0, 0, 1, then it will just be
I mean a
0.
two-dimensional one.
What?
A two-dimensional one.
Yeah.
0, 1, and another line would be 1, 0. Yeah.
Just get a sponge here. So now you want to take the minimum over x is 0. Or what?
It's the same.
The same as here, so with x is 0.
So, okay. Okay, got it.
So then you will again like take the minimum here and take the minimum here. So in both cases the minimum is going to be 0, so you just get an error with 2 zeros. Okay?
So when you take x is 0, it just compares the columns. And
Exactly.
the minimum and, okay.
So it's just like, it's a good way not to really think about NumPy arrays like too much in terms of rows and columns, because this only works for two-dimensional arrays. In the end you probably like have, I think you can have up to 64 dimensions of array, which is probably gets unwieldy, but you definitely have often more than 2. So therefore it really makes sense to think about, okay, this is always the axis that will be lost afterwards, after I make this reduction operation. So because I said like 0 is the first thing, and like the first index I provide selects the row. So afterwards, I will not be able to select the row afterwards because I have reduced the row. And so the same basically goes for if I make x is 1 here. So with the second argument, I always select like which argument do I have from here, and therefore I will take then the minimum or the maximum or whatever over each row. Okay.
But will it jumble the rows if the minimums of, for example, as you just said, like, if we would change the 1 and the 8 and then search for a minimum again, would it return 0, 8, 0, 8, and would it still return 0, 1, 2? Despite
In the case of x is 0, x is 1.
x is 1.
So if we now, okay, let's first so if we would supply x is 1, the minimum would be 0, 5, 22, right?
Okay.
So now if we switch 8 and 1, in this case, of course, yeah, it doesn't make any difference.
Yeah, but if the x is 0.
Yeah, so again, okay, if we have x is 0 and we take...
No, it would make a
Oh, yeah.
difference. So now it's 0,
Oh, yeah,
1 and
sure,
22.
and it's 1, that's true.
Yeah.
Okay, yeah, true. So if we have x is 1, then this would be our first minimum, this would be our second minimum, this would be our third minimum. Yeah, good point.
Okay. So it's not bound to the specific order at least.
No, it always really looks in like each dimension and then sees, okay, what is actually the minimum.
Okay.
Yes?
And if you have like 3 dimensions now in like axis is 0, would you also take would separate the 2 dimensions then? Or?
Yeah, then it basically becomes hard to draw, but so the effect would be similar, that then we would take the minimum over basically every time a 2-dimensional array. So if we have here x is 0, and we have a 2-dimensional array that we do the operation on, then we just like look in a basically 1-dimensional array, what's the minimum. If we now have originally a 3-dimensional array, then basically by choosing the first index, we select always a 2-dimensional array, and then we take the minimum over that. So, yeah, so I mean, like we could try to draw a simple 3-dimensional array. So let's maybe just make a 2 by 2. So we have, and first this, let's make it 2, 4, 6, and 8. So this would be our first dimension, and then below that we have, I don't know, 3, 5, and then 7 and 9. So now if we close this properly, so now if we take the minimum over x is 0, so basically with selecting the first index, we will select like whether we look here or whether we look here. So basically by taking the minimum over x is 0, we would take the minimum over this whole array and over this whole array. So we would get something like 2, 3. So I guess this is really the point important to understand, because by saying, okay, give me the minimum over this respective axis, I always reduce this axis. So whatever I could select before, by basically putting in this respective index at this position, I will not be able to choose later on this index, because I basically did the computation over everything that was returned by this. So, yeah, I mean, it's like in this case, right? Yeah, I think so. But then somehow the x is swept. Okay. Oh, well, now I'm actually not totally sure if this what I just told you is true, to be honest. So I would suggest we just try it out, right?
Can you put the bots down?
Oh yeah. So if we make an array, and say, so what did we have here? Obviously can see it again. So we have 2, 4. And then 6, 8, and then below that we have this, and then
The second row is missing one opening one.
here, yeah. And then
And also
finally missing the closing one. So like this. So this would be our 3-dimensional array, and now if we take the minimum over x is 0, okay, it will just reduce. So it will basically take then the minimum over here and over here.
I mean, you said it yourself, it's like the axis that's gone is the one you specified. So it has to be like has to be 2 dimensional.
Yeah, exactly.
Can you try it with axis equals 2?
So yeah, this should also work in this case. And then we would like basically compare always this here, right? Like the comparison between 2 and 4, 6 and 8, and then 3 and 5, and 7 and 9. Okay. Yeah.
I don't understand why you get 4 numbers when you do it for axis equals 0, because there's only 2 arrays for axis 0, so to say.
Yeah, okay, so this was, I think, like wrongly explained by me, so it will not like basically take everything that is indexed by axis 0, but like will just remove basically the ability to select based on axis 0. So if we do like this, basically index with the first argument, we could basically select between this and this. So and then if we do it here on axis 0, we should basically make the comparison here between 2 and 3, 4 and 5, 6 and 7, and 8 and 9.
Could you swap, for example, 8 and 9 in the original array and then run it again?
So in the best case, this shouldn't affect the result, right? Because again, we make here the comparison then between 9 and 8 and 9 here, and still the minimum should be 8. Yeah, so this axis argument is a bit tricky to understand, even for me. So, but I hope this gives you like an intuition about how this works, and once you understood it, it's pretty powerful, I guess, to do computations on your array. So we basically just continue with other reduction operation that exists. So there's also the possibility to take the maximum.
Could you push down the back button?
Oh yeah. Right, so again, if you don't specify any axis, just like compute it on the whole array. If you specify an axis, we'll try to reduce this dimension and compute the maximum on this. And then another reduction operations are things like, for example, the sum. So you can basically, instead of just choosing the column from which to compute the minimum, you can just compute the sum over this column. So either you compute the sum as in here, for example, over the whole array, or again you can specify an axis over which you want to compute the sum. So just to basically get the original array again, it looks like this. And then obviously if you add up all numbers, it's 120. And so if we basically do it with axis 0, it will take the sum row-wise, no, column-wise here, and will give us these values, and otherwise will take it row-wise if we specify axis 1. So, and then finally, like a lot of these reduction operations also exist as methods on the array object. So instead of calling np_sum of array, you can also call array.sum, and it will give you the same result. You can also specify an axis argument here. Also gives you the result, but this does not work for all NumPy or mathematical function that exists. So, for example, with the logarithm, it does not work. So yeah, I would say like probably it's easiest if you always use the NP version, but depends on what you like better. So okay, now we come to another tricky topic, broadcasting. So as you already asked, what happens if we try to add two arrays that don't have the same shape? So then NumPy would try basically to extend the arrays in a way that the shapes match up. And then, so this process is called broadcasting, and there are basically 3 rules that govern how broadcasting works. So we can look at this example. So let's say we have a array of shape 3, and then there's a scalar which can be viewed as of shape 0. And what does happen? So the first thing that is always done is that you try to add a 1, or basically try to add dimensions of 1. So maybe it's also more convenient if I try to draw this on the board. So let's say we have like this array of size 3, and then we have like just a scalar that we want to add to this. So this has in the shape 3, nothing, and this has just the shape of basically nothing at all. So basically what first is done is that you say, okay, we basically try to add dimensions of shape 0. So basically you can use as drawing square brackets around this thing as long as we have enough dimensions. So afterwards this will be an array of dimension 1, nothing. So then at least we have the same number of dimensions in both arrays. So what then happens next is that we try to extend this array. Basically every dimension that has a shape of 1, we try to extend so it has the same size as this. So afterwards we basically would extend this by making the 1 into a 3. So therefore we would basically copy this as long as necessary, so like here, and then you would have an array of 3, nothing. And now obviously you can add these 2 arrays together because they have the same number of elements. So this is basically like the 2 rules that always apply. You basically first try to extend the number of dimensions, and then you try to extend the shape, so by basically just copying the values. So it's basically the same thing, right? You have a 2-dimensional array and you have a 1-dimensional array, so you would add basically 1 here in the first dimension and just extend this. And also it works like if both arrays have basically different shapes, like here where you have like a shape of maybe 1, 3 and 3, 1, so to say. So you can also first make the 1 first 2-dimensional and then extend both, and then you can also add them together. So this is one example. You might, if you have 2 arrays like this and you add them together, like 2 1-dimensional arrays, you suddenly get a 2-dimensional array. So, and if this does not work, then just an error is raised. So we'll have some example here again. we have a two-dimensional array like this, then we have a one-dimensional array like this, and then what obviously happens is that this array is basically extended 5 times here and added at every place here. So here in the first column, everywhere 0 is added, here everywhere 1 is added, and here everywhere 2 is added.
Can it only broadcast the size of the dimension as 1?
Sorry?
Would it be, so if you had 0, 1, 2, 3 plus 3, 3, would it then make
You mean like from the shape? Or
if you have shapes 4 nothing and shapes 2 nothing, would it broadcast the 2 nothing into 4 nothing by repeating?
so like this. So this would not work because like the first thing that is always tried if the number of or will it work? I don't think so. So yeah, basically the first rule is basically add once here as long as the number of dimension does not add up. Once the number of dimension does add up, basically extend the ones there so they fit the other array. So if you have a 2, this does not work.
That's okay.
Yeah, so and here we have an example that this does not always work. So if we have like this array has a shape 5, 3, and now if we try to add an array of shape 4, then just the broadcasting error is raised. So okay, it says value error, and then could not broadcast operands with shape 5, 3, and 4. So this does not try to completely munch together everything, but should be somewhat reasonable. Yes?
I just have a quick question about multiplication again. So there can be 3 different kinds of multiplication in my head. There can be a multiplication where you take in 2 matrices which have the dimension m times n. So you take 2 cases of matrices with m times n, and you give out m times n matrix. So you do like a component-wise multiplication, and this you can do with just normal stuff. And if you want to do a matrix multiplication, so m times n and then n times l or something, and gives out n times l, then you use this add sign.
Exactly.
And if you want to do a scalar multiplication, then you just use a star and nothing.
Yeah, then you just have to use the star, because then again, like basically the scalar would be broadcast into the same shape as the matrix, and then everything would be multiplied element-wise. Okay. Yeah, so then we come to the topic of indexing. So NumPy provides a lot of different methods to index your arrays, which are very convenient and actually pretty powerful. So first thing that we'll look at is multi-dimensional indexing, so to say. So you know from Python list, like if you have a list of lists, you can access element by basically providing 2 indices like this. And I mean what this does under the hood is basically first pull out the first list here at the index 2, so this list, right, and then you would index this list again. So under the hood, this was basically translate to so if you do this, right, this would
blackboard again.
Sorry.
Blackboard.
Okay. Yeah. So what I just wanted to say, like if you have a 2-dimensional list, and then you do this will basically just translate to and then get items. Not yet familiar with writing on the board. This is get, this is item. And then you would call this with 0. And then on this again, you would call again get item of 1. So there you basically are 2, like first you pull out an object, call a method on it, then you again call a method on it. So, and this has, of course, some overhead, so NumPy avoids this by giving you the opportunity to basically supply 2 indices at once. Yes?
I think the question was if you could turn the blackboard down.
Yeah, sorry for misinterpreting this. Yeah, so NumPy basically provides you the opportunity to provide two indices at once. So instead of basically giving this two square brackets, you can just give a single square bracket and basically say 2, 1 at once. And then you also get like the same result if you just have an array. And basically if you want all items from a single dimension, you can just give a colon. So in this case we make a little bit larger array, so 81 values. And then we just say, okay, we want from the first dimension, we want everything. And then from the second dimension, we just want the first. So again, like the first dimension would be this. So we take everything from here, and then from the second dimension, we only take this. So we get in the end then a one-dimensional array with the values of this column here. And basically, again, all the standard slicing stuff that you know from Python does work. So we basically can provide a start and stop. And this way, basically slice out ranges from your array. And you can also provide a step argument. So in this case, right, we go from the second to the seventh and then only take every second one. So we take this, and then it ends. And yeah, what you should be aware of that basically all these things that are indexed here return views of the original array. So that means that if you first create an array and then you basically have some memory that represents the values there, and then if you slice from that, NumPy doesn't copy all the values because it would be very expensive, but it just says, okay, we just look at this block of memory in a different fashion. So we can look at a two-dimensional array just at a single row. We can look at it as a one-dimensional array, for example. So that also means that, for example, here we would create a slice from our array, and then we basically set the whole slice to 0. And then in our original array that we did not explicitly change, suddenly the whole column is 0. So this is something that you should be aware of, that if you slice out stuff, it's only a view, and if you really want to process values in a different fashion, you need to copy them explicitly. But otherwise, it's very convenient if you want to assign values. So then you could also write something like, say, okay, this, or let's make it then for different column. You could also directly assign 0 here, and then say, okay, now also the whole column is 0 right away. Okay. So and then if you have a lot of dimensions and you want to basically get all of them, you can use the so-called ellipsis as a shorthand. So there's this 3 dot thing, which is actually a Python object. I think like if you type this, it says you ellipsis. And so here we make a 4-dimensional array using the stack function that we'll also shortly look at later. That is something that just, okay, we have a bunch of 3 times 3 times 3 arrays, and we just stack them together on a new axis. So we get a 4-dimensional array that then looks like this. So basically the first dimension tells us whether we have this block, or this block, or this block, and then the other dimensions say, okay, this block, this block, this block, which row, which column. So now if we just say, okay, we want to, so this is our shape. Now if we say we want to have all the 4s, we could either say, okay, give me, in the first dimension, give me number 3, which would be this, and then in all other dimensions, the whole block again, the whole block again. So of course with a certain number of dimensions that can get a little annoying. So therefore you can also provide the ellipsis and just say, okay, it basically fills up with everything with colons that is left here. So you can also say with 3 and then everything else. Yes?
Couldn't you just say 3? Is that the same?
Okay, in this case, yes. Probably that's not the best example then. But could also be that you want to have this somehow here.
Okay.
Right, and then not sure what it will actually spit out now. Index error, because we don't have so many. Let's go like this. Yeah. Then you could, for example, always index the first one here. And you could also specify something in front, and then ellipses and then something in the back, so it will just fill up everything in between.
And can you put it in the middle, like
Yes, exactly. So you can do something like this, and just then it will be. So this should be the same as doing this. So it tries to fill up basically the whole dimensionality with colons that you did not specify. But you can only specify one ellipsis per index, so you cannot say one ellipsis, because you don't know, and it does not know which dimensions actually to fill up. Okay, then another thing that is kind of cool is fancy indexing. So instead of basically just saying starts and stops and steps and so, you can explicitly give coordinates or basically tuples of indices that you want to index. So here we have an array that goes from 10 to 18, and then we have an array of indices. So we have 1, 4, and 5. And then we can just pass these indices array to the getItem call and basically retrieve the 1s, the 4th, and the 5th element from the array. And interestingly, if you specify indices in a different shape, then the resulting array that you get from here will have the same shape as the indices that you provided. So if you do this, then you get the same values because you provided the same indices, but the resulting array is now a 2x2 array. And yeah, so if you have a multi-dimensional array, like for example this, then you can basically specify first the x indices and then the y indices. So it would be actually the y indices first. But then you just provide like separate arrays for basically each dimension, and then you get like the thing at 3, 1, which would be this here, and the one at 1, 2. So this is 1, this is 2, so you get 4, 2 right here. So 4 and 2. This is 4, this is 2, so you get 14. Okay. So then something that is probably even more useful is masking for indexing. So instead of providing just the explicit indices, you can also provide an array or logical array of the same size and basically specify which values you want with a true and the values you do not want with a false. So let's again make a simple integer array. It just goes from 1 to 5 here. And then we make a different array of a type Boolean because we just provide Boolean values. We'll automatically determine the D type to be Boolean. And then we say, okay, we want the first value, we want the third value, and the fifth value. We don't want these. And this will be our mask. And then basically if we put in this mask to the getItem call, you will only get the values that basically had a true in the mask. So and this can also be used for assignment. So in this case you see like the resulting array is smaller than the original array because the values that had a false here just did not get returned, but if we basically assign something directly, then the array will stay in the shape it had before, and all the values that had a true here will get a 10, and all the others will not be affected. And so what is really convenient, you can basically create this mask by using the vectorized versions of logical comparison operators. So if we make an array, and then we say we want the array compared to 2. So basically say as greater 2. We get an array that has get a Boolean array that is true at every value where basically this array is greater than 2. So the original array, and you can also show it again here. Look like this. So basically these two values are not greater than 2. That's why we have a false here, and these values all are greater than 2, and that's why we have a true here. So this is somewhat simple, and then you can just basically index your array based on this mask that you created using this logical comparison operator. So in this case, it's an easy way to get all the values from your array that are greater than 2. And you can make this even shorter, right? You don't have to store this in a variable. You can just basically in the get item call just provide this condition like this, and then you get the same result. And then you can also combine different masks to basically create more, to evaluate more complex conditions. So in this case we have a condition smaller or equal to 4, just using this operator. And then we see, okay, only the last value, which is 5, is not smaller or equal to 4. And then we basically can combine two masks, and basically we have all the logical operators that we know. We have AND, we have OR, we have NOT. So in this case, if we say AND, we have everything that's greater than 2 or smaller or equal to false. So in this case, these are only these two values, because here it's smaller than 2 and here it's no longer smaller or equal to 4. So but for these values, the condition still matches. So be aware that you really need to take these operators, which basically provide the bitwise logical operators, and don't do this, because this will try to evaluate the Boolean value of the whole object here. So if you do this, it will basically try to assign the Boolean value of greater 2 first, and then basically do a conjunction with the Boolean value of smaller or equal 4. So in this case it does not work, because it says, okay, the truth value of an array with more than one element is ambiguous. It means like if you have an array that has more than one value, it could be either true or false. It's not like Python list, where empty list is false and everything else is true. In this case you really need to reduce your array to a single truth value yourself. So what you can do in this case is use things like all or AND, where you basically say, okay, are all values in my array true, or is any value in my array true? So okay, and then once you have basically done this bitwise comparison here, you get a new mask, and you can again index your array. So now you get all your values from your array that are greater than 2 and smaller or equal to 4, which are 3 and 3 and 4. You can also use OR, bitwise OR, which is this pipe symbol here. So in this case you get all values that are either greater 2 or smaller or equal to 4, which are all the values. And you can use this caret for exclusive OR, so the ones that are either greater than 2 or smaller or equal to 4, which would be this. And you can also negate a mask using this tilde sign. So in this case it would be everything that's smaller or equal to 2, which is not greater 2. So in this case it's only 1 and 2. So and yeah, then finally we have something on extending arrays. So there's this thing called np new access. So and basically you can use this to add dimensions to your array without adding values. So for example, if we have a one-dimensional array like this, you see, okay, it looks like this and the shape is 5, nothing. And now if we basically index using np new access and then everything, we'll get a two-dimensional array out of this. So what this basically does is, in the first dimension, it just adds basically square brackets around what already is there, and then keeps the array as it is. So you can also swap these arguments, and then you get an array of shape 5, 1 instead of 1, 5. So then suddenly you have something like this. So this is sometimes necessary, like if broadcasting doesn't work and you need a basically bunch of ones and place it where broadcasting will not create it automatically for you, then you can do something like this. So and then, yeah?
Can you always add only one axis, or is there an option?
Well, I think you should also be able to add multiple ones.
Okay.
So yeah. So instead of new axis, you can also put none here, and then it will be interpreted as none as new axis. So depends on what you like better. So yeah, and then a few things on combining arrays, and just very quickly. So just in general, we actually should not really try to combine arrays. because the thing is, NumPy arrays, as I said, like creates really the whole thing in memory. And now if you try to basically put two arrays together, it has to copy all the values that are already in the array. So what's much better is basically before you allocate your memory, you should think about, okay, how much values do I actually need, and then basically maybe initialize it with zeros, and then just fill in the values while you do your computation. If, however, for some reason that's not possible, you can use functions like concatenate, stack, or append. So basically, for concatenate, it just takes a tuple of arrays, and then it will just put them together in a single array. For stack, it basically does not try to put them together in the same array or like in an array of the same shape, but creates an array of a new shape and joins them along a new axis. So in this case, we had like two one-dimensional arrays. Now we get a two-dimensional arrays. And for append, you put an array and then a bunch of values, which can also be an array, but could also be a list. But then the result is the same as concatenate. But in general, rather try to allocate first and then fill in the values, then first create a bunch of small arrays and then put them together later on. Yeah, so I think this is actually what we have on NumPy for today. If you want to hear more, here's a link to a very good online textbook that you can access for free by Jake van der Plas. He's a very active member of the scientific Python community. And yeah, here's a whole basically book written in Jupyter Notebooks, also basically covering many topics that we have here in the lecture. So you should definitely take a look here. And then there's also a YouTube tutorial from the latest SciPy conference. So often like these SciPy conferences are very good resources basically for anything related to scientific Python. Often you get there really tutorials by the developers of the libraries themselves. I guess this is not the case in here, but this is like then really much more longer and more elaborate tutorial than what we have time to cover here. So if you want to review any concepts, you can have a look there. So with this, I would just basically talk about the homeworks that you have this week, because we have some time left. So we basically have like we have two tasks this week. So we have again a simple or more or less simple task and a bonus task. So for the simple one, you have like last week you have like 4 small exercises that are more or less unrelated. So if in the first one is related to indexing, so you should create an array that has a checkerboard pattern, so just zeros and ones alternating, and with the 0 in the top left corner. And for the second one, this should be probably solved by masking. So you get an array with mixed values, both positive and negative, and then you should replace all the negative values with positive values, and they should be replaced by the mean of the positive values. So you can think about some conditions to evaluate basically this and get these values out. So the third one is about calculating pairwise distances between vectors. So basically what you get here is an array of 2-dimensional vectors, and then you should create a n by n distance matrix. So this basically, if you get an array like this, so this is one vector, and then this is your second vector, then you, in the end, you should create so let's say like this is vector 1 and this is vector 2. So then you should create a distance matrix, and then this entry should basically contain the distance between vector 1 and vector 1, which is always 0, and then this here should have the distance between vector 1 and vector 2, which is something, and then this would be the same value. So the matrix should be symmetric because you should calculate the Euclidean distance, which is always symmetric between vectors. And then again, this here would be 0. And then, of course, you will get much more vectors than just 2. And then for the fourth exercise, you should implement a moving average, where you just get a 1-dimensional array, and then you have a window, and then basically in each window you calculate the average from all the values that fit into that window. That's for that, and then you also have a bonus task this week again, and this is basically just a single function that you have to implement, but that is a bit more involved. So you basically need to think about slicing and indexing arrays. So we want you to write a function that takes an array and a shape and then a center and then fill either none or a value, and then you should basically from this array you should basically slice out a subarray of the shape centered at center. So so in this case this would be an array, and then it would be probably provided like shape 3 by 3, and then you basically have a center at like, yeah, this is 2, 2. So then you need to slice this out, and then there could be places where this does not match, where basically you want to slice a bigger subarray than what we can actually slice at this center. So if fill is none, then this should be just cut off, and if fill is not none, then basically these values should be filled by the filled value. So in this case here fill is 1, so you should slice this out, and these should be 1s. Yeah, so let's say this is it for today. If you have any questions, then ask them now. Yes?
Just one regarding the test file system. Last week I couldn't do more works. I tried to do them, and then I ran PyTest, and it just tested the Gatsby thing for me, and then the rest it didn't test. So,
As soon as you add the Gatsby, it tests everything.
okay.
So
I was just wondering how to do that. Okay.
So that was an error on my side. So PyTest uses assertions to check if everything's fine, but only assertions in a function test underscore something is treated as a PyTest assertion. And I have this one which tests if the module exists outside of a test underscore function, which is why it was a normal assertion, which is I just threw a normal error instead of PyTesting carefully. Shouldn't be the case now because the files are there.
Yes, exactly. So this time we provided all the files you need and also the function stubs with the arguments, and so you just have to provide the code, so there should be less confusion on what to put where. Okay then, thanks, and have a wonderful 1st of May tomorrow.